Here the second type is bulk modulus, and we represent bulk modulus by K, and it is defined as the ratio of volume stress to the volume strain. Okay. Now let us try to explain bulk modulus by taking one example. Here what I am going to do, I am going to take one object, then I am going to apply force in all directions. I am going to apply force in all direction. Then what happens? This is the area of cross section. Then after applying this deforming force, this body undergoes deformation. That is, there is change in volume of this object. That is, this is the change in volume after applying this deforming force. Let us suppose it is V2, and this is the V1 is the initial volume, and change in volume, that is delta V, is given by V2 minus V1. And we know that stress is given by F by A, and strain is given by delta V, that is change in volume divided by original volume. Here also same, where I am going to apply force, that is different deforming force values. Initially what I will do, I am going to apply force from 1 Newton to, let us suppose, 8 Newton force. Then what happens? If you remove this deforming force, this body will regain its original size and shape. It is due to the property of elasticity. Then what I am going to do, I am going to apply force, that is 9 Newton to 12 Newton force. Then what happens? Then also there is decrease in volume of this object, but at this time this body is not going to regain its original size and shape. It is due to the property of elasticity. Now what I will do, I am going to plot graph for this situation. Then we are going to get this kind of graph. Then what we will do, along y-axis we have taken volume stress value, and along x-axis we have taken volume strain values. And here same, from 0 to certain elastic limit, volume stress is directly proportional to the volume strain, and above elastic limit, volume stress is not directly proportional to the volume strain, and after some point it will break into two parts. Okay, here we define bulk modulus, that for this case volume stress within elastic limit, here within elastic limit volume stress is directly proportional to, that is, within elastic limit volume stress is directly proportional to volume strain. And here we are going to remove this proportionality sign. Then here we are going to remove this proportionality sign. Then volume stress is equals to K into volume strain. Then K is equals to volume stress by volume strain. Here you can see that K is equals to volume stress by volume strain. If you substitute volume stress, that is, volume stress is nothing but F by A here, but we know that F by A is equals to P. It is the force per unit area is nothing but pressure. Here in the place of F by A, we are going to substitute P, that is, P is pressure divided by change in volume by original volume. If you interchange terms, you will get original volume into pressure divided by change in volume. And SI unit of bulk modulus, it is and SI unit of bulk modulus, that is K, is Newton per meter square. Here bulk modulus tells us that compressibility of fluids or solid, and also if something is highly compressible, it has low bulk modulus, and also if something has low compressibility, it has a high bulk modulus. Here we have taken two examples. In the first case we have taken gases as an example, and in the second case we have taken diamond. Here you can see that these gases are highly compressible, that is, it is having low bulk modulus, and for diamond it is having low compressibility and it is having a high bulk modulus. Bulk modulus is simple. Within elastic limit, volume stress is directly proportional to the volume strain. Then what we will do, we are going to remove the proportionality sign, and in the place of proportionality constant we are going to substitute K value. Then K is equals to volume stress by volume strain. Okay, now let us see the next type of elastic moduli. The third one is modulus of rigidity, and it is denoted by symbol eta, and it is the ratio of shearing stress to the shearing strain. Okay, now let us try to explain modulus of rigidity by taking one example. Here what I am going to do, I am going to take one object, then I am going to apply force tangentially. Then what happens? Let us suppose it is point A, B, C and D. After applying this deforming force, this point A, point B will shift into next point. That is, it becomes A dash and B dash. We have already discussed this concept earlier by making an angle theta. And here also same, we are going to perform a same experiment. Initially what I am going to do, I am going to apply deforming force from 1 Newton to 8 Newton. Then what happens? Due to the property of elasticity, it will regain its original size and shape when we remove this deforming force. Then I am going to apply from 9 Newton to 12 Newton force. Then what happens? This body will change its, then this body undergoes deformation, but when we remove this deforming force, this body does not regain its original size and shape. It is due to the property of plasticity. Then if you increase force further again, then also same, this body will break into two parts. When we plot graph for this situation, we are going to get this kind of graph. That is, along y-axis we have taken shearing stress values, and along x-axis we have taken shearing strain values. And here you can see that from 0 to certain point, that is up to elastic limit, shearing stress is directly proportional to the shearing strain, and above elastic limit, here shearing stress is not proportional to the shearing strain. It is due to the property of plasticity. Then after plastic region, object will break into two parts. That is, it is the breaking point. Here we define modulus of rigidity that within elastic limit, shearing stress is directly proportional to the shearing strain. Then here shearing stress is proportional to the shearing strain. We are going to remove this proportionality sign. In the place of proportionality sign, we are going to add proportionality constant, that is shearing stress is equals to eta into shearing strain. Then if you interchange these terms, that is eta is equals to shearing stress by shearing strain. Then we know that shearing stress is given by F by A. Here this is the original length, and shearing strain is given by, this is the change in distance. Here also this is the change in distance. A dash gives us change in distance, and volume strain is given by, and shearing strain is given by delta x by original length. Here one more thing we need to discuss, that it is the 90 degree, then tan theta is equals to delta x by L. If tan theta is nearly is equals to theta, then theta is equals to delta x by L. Here what I am going to do, I am going to substitute shearing stress value. Shearing stress is F by A. We have substituted F by A divided by shearing strain value, that is delta x by L. It is nothing but theta. We have substituted theta value. Then if you simplify this equation, we are going to get F divided by A into theta, where F is the amount of deforming force applied and A is the area of cross section, theta is the angle, theta is the shearing angle. Here modulus of rigidity or the shearing modulus is used to determine how bendable materials will be if they are sheared. That is, let us suppose here I have one material, I am going to apply some shearing stress, then what happens? This body will bend. Let us suppose in case of this material, if I taken a rubber band, then what happens? It will completely bend. Then here modulus of rigidity gives how much a material will bend when we apply a shearing stress. Here in this chart we can see that shearing materials for aluminium it is 25 gigapascal, and for brass it is 37 gigapascal, and for steel it is 83 gigapascal, and for tungsten it is 160 gigapascal. Okay, what is modulus of rigidity? It is simple ratio of shearing stress to the shearing strain. Okay, so far we have discussed three types of elastic moduli. The first one is Young's modulus, and second one is bulk modulus, and third one is rigidity of modulus. In the first case we have applied force normally. In the second case we have applied force in all directions. In third case we have applied shearing. In third case we have applied tangential stress. Okay.